this was the problem immediately after I burned all those 5 musketeers, all those 5 MOSFETs. Immediately after I burned them, I made this circuit that you are seeing here. Pretty much, this is the simple switch. This is what a MOSFET should do, switching, exactly like a switch, like this, you see, here on the oscillogram. So I took this resistor and I view it in scope. You can see here the name resistor 10 ohms. Let's perform the experiment. First, I will close it for a certain duration of time, and then I will release it. And I will pause the simulation and read the values that I'm getting over this resistor. So I'm getting this 5 volts, and here is the current that is passing through it, 500 milliamps. So I'm having 5 volts times 0.5 equals 2.5 watts. I don't know how to set up the amperage from this power supply in this simulator. I don't know how to increase it. Let's say 5. No, 5. The voltage is fixed, and you cannot tweak the current through it. These are the values that I tested my MOSFETs previously when I burned them, and I got 5 amps here. I was getting over it. And check this out. If I'm changing this 10 ohms into 1 ohm, exactly like I was having it last time when I burned the MOSFET. Let's run the simulation. So when I'm doing this switching, you see, I'm leaving it for a period of time, and now I'm closing it and stop it, and now I'm getting still the 5 volts across this 1 ohm resistor. But look at the amperage, it's 5 amps, exactly as I was getting it last time when the power supply was switching and from voltage to amperage when I was connecting, when I was performing this switch, when I was enabling the MOSFET. And it's 25 watts. At this point, it's 25 watts over this resistor, but probably, I'm not completely sure what is the wattage over the MOSFET, but the MOSFET, it is having a tiny little bit of resistance, internal resistance. So this is what I wanted to show you, that I was getting this 5 volts, but also this 5 amps over this resistor and over this MOSFET, because he was letting all this power, all this current passing through it, and it was too much. And when I'm continuing the experiment here, and I'm switching again, but this time with this 100 ohms, and I'm stopping it. Here is also 5 volts over this 100 ohm resistor, but look at the amperage is 50 milliamps. So this is the new rule that I created here. It all depends on this resistor load to be high enough to be able to limit the current low enough. So in case 1, if the resistor is 1 ohm or lower than 1 ohm, it may be 0.1, 0.1 or 0.2 or 0.5 ohms, basically a shunt that you are having here. The current will be too high and it will damage the MOSFET. But actually the MOSFET didn't got damaged by those 5 amps that I was passing through this 1 ohm resistor. The MOSFET got damaged by the switching of the power supply when it was switching. So I should probably put a note here that in this document that I'm having here, in this save file, to not damage the MOSFET is to avoid that kind of switching from the power supply, not let it or not leave it switch. If you see it that is switching from voltage to amperage, then turn off your experiment. It will not destroy your MOSFET from the first switching from voltage to amperage, but if you are doing it rapidly or very fast, the switching of the gate of the MOSFET at this 1 ohm value, that power, it will definitely fuck up the MOSFET. It will melt it inside it. Okay, like I was having those issues before. Case 2, if the resistor load is 10 ohms, this line here, the current is still high, but not that high that will damage the MOSFET. Here it says that not tested, only in theory. And actually with this experiment, I did test this theory that I'm having here. And at this particular value, at this 10 ohms, I didn't get that switching of the power supply from voltage to amperage. That's the thing. I'm not sure exactly when the power supply, at what resistive value is switching. I should exactly test it for that particular situation when, when it's not switching anymore. The lowest value of the resistance that you can put to not make the power supply switch from voltage to amperage. I actually put my power supply over the 10. Let me change this back to 10 here. Actually, this is my power supply, and I put positive and negative rails of the power supply directly over this 10 ohm resistor, and I turned the knob to 5 volts, and I was waiting for the power supply to switch to amperage, from voltage to amperage, and it did not switch to amperage mode. But if I'm changing this to 1 ohm here, to 1 ohm like this, the power supply will switch from voltage to amperage, and it is entering in short circuit mode. And when it's entering in this short circuit mode, it will switch frequently its power lines, and that is killing the MOSFET pretty much. That's the problem. The last case here, if a resistor load is 100 ohms, let me change this to 100 ohms because it's about it, or higher than 100 ohms, the current is low to very low, like you've seen here, 50 milliamps, which is almost nothing, and has very low chances to damage the MOSFET. The MOSFET will not conduct the 5 amps anymore like it was doing it in 1 ohm situation, but it will be protected from the switching of the power supply. That's what is about all this saving, all this file that I created here. And based on this, let's say, principle that I created here on this saving file, I actually performed this last test, and it did work perfectly. So I did get a bump, a knock in my head with destroying my MOSFETs the last time, but I didn't give up. I persevered, and I stopped to think about it. It actually passed a couple of days until I get to these solutions that that you are seeing right now and the experimentation that I just did. And it wasn't fast. It did put me to think quite hard, because it's so basic and so simple. You have to get low to this level and to start really hard to think. Hardcore thinking is like that. And it's nice when you figure out what the problem is and how to get around it and how to use it in your benefit, pretty much. So this is it. This is the actual starting of the experiment, doing it in simulator here, and then getting it into the reality and playing and testing in reality and observing in reality what is what. Okay, that's it.
All right, hello everybody. I'm very happy because I took it a bit more slowly. The last time I was a bit too impulsive, maybe too brutal, way too brutal, and I really didn't know my tools that I'm working with, especially my power supply, my variable power supply that is performing this switching from voltage to amperage, specifically when it's detecting a short circuit between positive and negative rails. And that switching between these two is creating a pulse. I actually demonstrated that pulse that is happening. The next logical idea that I had was to not let it switch there. So as long as it's not switching there is perfectly fine for this testing circuit that I'm having here. That's actually a very big problem when it's doing the switching. But as long as it's not switching, everything is fine. I'm having the exact same circuit, but I don't have this voltmeter here and this capacitor. I should probably make another circuit. I will post the circuit later. I searched for all my resistors that I had, especially the brand new ones, and nothing really fit the bill, let's say like that. So I made some tests. This is a scrapped resistor that I'm having here, 160 ohms at 16 watts. It was a bit too big. This was the original 1 ohm 5 watts that the power supply was switching from voltage to amperage, because this 1 ohm is seeing it as a dead short circuit over the power lines. The next one, I actually measured this scrapped power resistor that I'm having here, because every data on it was erased by time or by someone bad. And I measured it as 34 ohms at probably at 5 watts. I don't know exactly if it's 5 watts or 8 watts or 10 watts. It might be, but I'm giving it by the ear. I'm giving it a 5 watts because it was resistive at 1 and 42 watts. It was like 50, around 50 degrees Celsius. So I tested this resistor originally. I was testing it, this 34 watts here, resistor here. And the voltage, I intentionally double it, 6.8 volts. So 34 times 2 is 68. So here 6.8 volts. It gave me 0.21, and I was expecting 0.2 amps, and I totally get it. So this is another way to test a resistor, the true value of a resistor with voltage and amperage. So originally I tested it at 3.4 volts. And I got 0.1 amps. So this is how you tell the exact value of your resistor. This is another way to test a resistor using your power supply directly. I hooked these two alligators directly here and here, and not with this circuit. So directly there, and I read those values. At 3.4 volts, I set the voltage to 3.4 volts, and I get exactly 0.1 ohms. And here is very close to it, very close. It's 34 point something. Is 34.5 maybe ohms, so that's why I'm getting 21 there. It should have been 20 exactly if it was 34 ohms exactly. But now it changed a little bit. Last time wasn't budge from 5.2 to get 0.50 amps exactly there, but right now it's very stable after more than 5 minutes of running. But look at the temperature over this poor resistor. Right now I'm taking the temperature over the resistor because this is the load resistor what I'm having right now in this circuit, and he is getting exclusively all the heat. And if you put your finger on this kind of heat, the skin will stick on the surface there. So you will have to peel your skin already stick on it. So it will drag and see the flesh and the muscles underneath. That's how hot it is at this temperature for a normal sensitive skin, human skin. So it's not advisable to put your finger on this kind of temperature because it will boil your skin and adhere it and stick it there. But here, if I'm putting my finger over this transistor, over this MOSFET, is absolutely cold, is ambient temperature cold, so it's no problem with it whatsoever. This was my American friend advice the last time we spoke, way before I did the other experiments, but right now it's very clear to me what is going on and at what a MOSFET is good at. A MOSFET, it is good to transfer the amperage, is exactly like a switch, and is letting the amperage through it like a normal, pretty much like this switch, is exactly like this switch. These two are two switches in this circuit. I was doing a big mistake actually the previous times when I was putting my probe over the MOSFET to probe the MOSFET temperature, but then I realized after I was taking some breaks and some pauses from all this experimentation, then I realized it occurred to me and I remembered actually and it's a pretty stupid mistake actually, but well, in a sense it wasn't that stupid because I didn't know what to expect from those 5 amps that I was having last time. So I remember that a MOSFET is a capacitor. That's why it's able to conduct such a great current through it. The gate is switched in a capacitive mode, and because it's behaving like a capacitor, it is not heating up. from all my experiments that I did so far, it's not really that necessary or correct to put a probe, a temperature probe over your MOSFET. But probably there are some cases that I don't know. I didn't test everything in this world that you can do, and there are some cases probably when the MOSFET will heat up. I didn't reach those cases or those experiments. I didn't make them yet. What I did here is very, very basic, very simple, just to drive a lot of power. And when I did the experiment with this resistor, with this 34 ohms resistor here on the first line, and I got this 1.42 watts. For a moment I wasn't that impressed on this wattage, on this 1.42 watts. It's not that great, you know, it's okay, 1.42 watts, but remember this guy when I tested it and I got only one single watt, exactly 1 watt, like 60 degrees Celsius or 80 degrees Celsius over it. I don't remember the temperature. This is a NPN BJT MOSFET. This is its name, 2N3773. This barely conduct anything, and it was heated up like crazy, while this is ambient cold, is letting all the power over the resistor. This is what is doing this MOSFET in that I'm testing it here, is letting all the power drop over the resistor, and the resistor is getting all the power over it. So this is the main role of it as a driver, current driver, pretty much is driving the current through it, and you can switch it and probably you can even dim it. From my general knowledge that I'm having using a PWM, or even with a 555 at a certain frequency will pulse the gate, and probably we will have a 50 duty cycle like that or something like that, you know, at half, and you can dim it in a test mode with even with a 555 in a pulse mode, or a specific circuit for PWM to dim the amperage that is flowing through the MOSFET. Probably in those cases the MOSFET will get hot, but in this case, when it's letting all the current through it without any dimming, with like a normal switch, it's performing excellent. Okay, so right now I'm having 146, but if I'm getting this off, interesting, I was getting a way more higher temperature without this clamp. Not really, interesting. But before, probably, I don't know why. Or maybe it's increasing. Let's okay, probably. Oh, only there in that spot, maybe, where it's clamped. Yeah, it was a bad idea to take it out because it was showing a very high value there. Anyway, let's do the experiment. So as you can see, I'm having exactly 5 volts and exactly 0.5 amps. So 500 milliamps there. And okay, that will increase probably to 148 as it was before. But if I'm doing right now the test, it will decrease the temperature. So let's do the same exact test that I did the last time. The last time I did this test with 5 amps, and when it was switching from voltage to amperage, and it burned my MOSFET. So I will do the exact same test right now with this configuration that I'm having here, having this 10 ohm resistor there with 5 volts and 0.5 amps at 2.5 watts over that resistor. So I will do this test like this. Do you see how I'm moving it like that, you know? And if I was doing it one time like this, the MOSFET was already burned from only one test of switchings like that. And voila, it is still the same voltage, the same amperage there. So that's my guide, that is guiding me if the MOSFET is dead or not. And let's actually power it off. So when I'm switching off the gate right now, that is shutting off. And now when I'm powering it on, it's turning on. So this is the same thing, this switch is the same thing as that, like doing it like that. But I am doing it like that also just to confirm that everything is incorrectly. Let me do the same switching experiment again. And as you can see, as you can understand, let me turn it like this and actually show the switching that I'm performing. Do you see how I'm doing it? I'm doing this very, very quickly. Probably it's a 10 hertz here of switching, or even less than 10 hertz. So I'm literally like that. And that should not more than 0.5 amps. You know, remember the last time it was increasing in amperage very much. Actually, it was going to 2 amps because it wasn't short, the MOSFET. That's why. But now, if I'm switching from here off, it's switching the amperage there at 0, 0, and now on and 0.5, and that's the, you see, off, on, off, on. This is the experiment. This is the proper functionality. This is how this MOSFET should function and should resist and should perform. Pretty much. That's my test what I'm conducting here. This is my demonstration and also verification, because I'm verifying this stuff and I'm trying to get to the maximum possible that I can drive it at. And I don't know yet what is the maximum, but for now it can drive this resistor at 2.5 watts, and this is phenomenal great. This is absolutely fantastically great. This is the main purpose of the MOSFET, to let all the power go on the resistor, on the load resistor, and not over itself, not to itself to get heat up, to let this power resistor to get heat up, all the power to be consumed by the load here. That's the idea, and I hope I was clear as mud, like usual. But I hope it's clear enough. Unfortunately, I don't like this temperature that I'm getting over the resistor, but I really don't care that much for the resistors if they get at this temperature. But usually they shouldn't get at this very high temperature, especially at 2.5 watts, which is exactly half of the rating of this resistor. This resistor is rated at 5 watts, exactly at 5 watts. So this doubled, it means 300 degrees Celsius when it's conducting 5 watts, or even more, because this will derate substantially. It will not be a linear transition. It will be like that, like a curve like this. It will go into the woods, into shit. It will be 1000 watts probably there when he will be able to actually conduct those 5 watts that is rated at. I don't know how they tested it at 5 watts, but probably they put some very large heat sinks over them. I don't know how. I have no idea. And nobody is showing all this stuff that I'm showing here. As dumb or stupid as it may look, or simplistic, this should be general knowledge for everybody. That's why I'm making all these movies, because nobody is doing this very basic experimentation with this stuff. This is a very, 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 very successful experiment what I'm conducting here, especially at this power driving. All this power driving that this MOSFET is doing compared with my NPNs that I had before. This was the toughest, this was the strongest, this was the best of the best, that of course from my arsenal that I'm having. But this is rated to here 150 watts actually. And this is a IRFZ is even less, is 95 watts. Really, this is a very, very good experiment compared with this NPN that it got extremely heat up, and this is not even warm. It is still remaining at room temperature and is conducting all the like I said, my skin will melt and stick to that. It's very, very hot. So it's delivering all the power to the load to be consumed specifically by the load itself and not by the transistor. So the transistor should act as a switch and not get over it any kind of heat, any kind of power dissipation. From this point of view, from this perspective, this is an exceptional experiment. It's the best experiment that I could make with the MOSFET so far. It's probably not that much amperage. I should actually take the data from the MOSFET to take the voltage and the amperage through it. Well, the amperage is the same, it's 0.5. But I should get the voltage over the drain and source of the MOSFET and calculate what is the actual wattage over the MOSFET. And I can do it right now actually, because I'm taking the voltage over it. So right now I'm at here at 2 volts. Let's see. Yeah, I should go to 200 millivolts, and I'm getting 12.5 millivolts. This is very good. This is actually very, very good. So because I'm cheap, I will use the same piece of paper here. Look there, 150 exactly by the book, with 5 volts and 0.5 or 500 milliamps. Wow, very, very cool. Very, very cool that I'm getting this very fixed temperature here. Very interesting, and it is smelling a little bit like a hot something that is hot, like a hot brick maybe. Hot cement, because this is a cement resistor. So 12.5, okay, millivolts. So 12.5 millivolts over the MOSFET times. So this is actually 0.012.5, yeah, volts times 0.5 amps equal, let's see. So 0.0125 times 0.5 equals, I like it. I like that number. Look at this number, I like it. Okay, so I'm getting 0.00625, and this means 6.25 milliwatts. So it's 6 milliwatts. 6 milliwatts over this transistor. Fantastic. This is very, very good. I really like it. That's why is staying so cold at ambient room temperature. Fantastic good MOSFET and a fantastic good experiment that I'm conducting here, because it's about how to perform this experiment the correct way and to show everybody how this should work, because nobody is showing or is telling this kind of experimentation that I'm doing here. I didn't find it anywhere. In all my research and all my searches over the internet, I didn't find absolutely anything related to this kind of problems that I'm conducting right now. This kind of experimentation, I didn't find it anywhere. If you find something like this, please do announce me and leave a comment there. But me personally, I swear to God, I didn't find anything related to this. This is probably, this kind of experimentation is probably done in very high prestigious faculties, universities like, I don't know, Cambridge, Massachusetts, whatever, but especially not Romania. This temperature that you are seeing here also is very, very important. All this time that I was filming and talking and explaining everything, it raised up and it leveled. It stopped at this temperature here. This is the maximum is raised at. And right now I'm having exactly 35 minutes of filming here, and it's actually is working even from before I was starting to film. So probably 40 minutes. Let me actually add this here. About 40 minutes of testing at this particular wattage, 2.6, 2.5. When I started the experimentation, it was not budging from this 5.2 to have this around 0.50 here. But as the temperature increased, something changed, and it did came to senses to 5.0 with 0.5 there, and actually 2.5 here. But let's say it started like that. Actually, let me correct it. In about 40 minutes of testing, and the temperature is 150 degrees Celsius over the resistor load that I'm having there. This 10 ohm, this here. This 10 ohm resistor. Yeah, fantastic. I really like it. But what I don't like is this extreme temperature that I'm getting. This is an extreme temperature, at least for my way of doing things. My politics about driving components doesn't matter what the component is, even if it's a resistor or transistor or a switch or whatever it is, whatever component it is, you should not get more than 50 degrees Celsius of that component running. It should run at cold temperature, at ambient temperature, or a tiny little bit over that ambient temperature, but not too extreme, not too hot. And this is too hot, way too hot. It's 3 times my rule of 50, you know. But beside this inconvenient, all this experiment, it is a very nice, I really like it, a very good success of driving all this power through that MOSFET to deliver it to that resistor there. I know the way I'm talking is not perfect, but I'm doing my best to express and to eventually to teach you how these things are working and how to properly drive a MOSFET and what to expect from a MOSFET when you drive it. What is the proper way of driving it? Okay, this is it. Thank you very much for listening and for watching and for paying attention to this successful experiment that I'm having here. And bye-bye from your favorite artist electronist, Mr. Q12 here. I say to you bye-bye and see you later, alligator. Bye-bye. Bye-bye. Bye-bye.